Okay, class, this is Team PCs. We're going to be analyzing a complete truss, which we have drawn up on the board. And we will be showing you how to solve for the unknown forces within the truss. I'm Justin Ovenchan, and my partner is over here, Josh Isaacson. Start by talking about the diagram and a little bit in the definition of the problem. We have three different lengths. Length 1, 2 is 3 meters, length 1, 3 is 4 meters, and length 2, 3 is 5 meters. And we have multiple forces acting on the object, or on the truss, and we know one of them. So the one we know is 1,000 newtons. It is downward on joint 1. We also have force right here on length 1, 2. We'll be solving for that, as well as the force in the y direction on joint 3, force in the y direction on joint 2, and the x direction on joint 2 as well. We'll also be solving for the compression of 1, 3 and the tension of length 2, 3. Now for a truss to be in complete static equilibrium, the sum of forces in the x direction have to equal 0. So adding up any forces going this way are going to cancel out to 0. Similarly, in the y direction, they're also going to cancel out to 0, which basically means that the whole object won't be moving. In our diagram, N is our symbol for internal force, and R is the reaction force. So in the y direction, we'll have a reaction force over here, etc.
So as Justin just explained, we're going to solve for the unknown forces on the truss. So we need to solve for the internal force between joint 1 and 2, the internal force between joint 1 and 3, internal force between joint 2 and 3, and the 3 reaction forces from the supports. For each joint, you want to set up 2 equations separating the total forces in the x direction and the y direction. So for joint 1, your sum of the forces in the x direction are going to be -3/5 times the internal force between joint 1 and 2 plus 4/5 times the internal force between joints 1 and 3, and that's going to equal 0. We found these two fractions by using basic trigonometry from the angles. So the cosine of alpha is going to be 4/5. So that's what we use for the x direction of joint internal force between joint 1 and 3. Also, we need to set up the sum of the forces in the y direction, and that's going to be equal to 1,000. This has to occur because the 1,000 Newton force from above is acting on joint 1. Also, for joint 2, we have 3/5 times the internal force between joint 1 and 2 plus the internal force between joint 2 and 3 plus the reaction force in the number 2 in the x direction equals 0. So that joint should not be moving. Also in the y direction, we have 4/5 times the internal force between joint 1 and 2 plus the reaction force number 2 in the y direction equals 0. In joint 3, we have -4/5 times the internal force between joints 1 and 3 minus the internal force between joint 2 and 3, and that equals 0. Similarly, in the y direction, we have 3/5 times the internal force between joint 1 and 3 plus the reaction force reaction force on joint 3 in the y direction equals 0. So basically what we've done here is set up the the sum of the forces in the X and Y direction on each joint. Now, using basic substitution, we can solve for each of the unknown forces that we have.
So after crunching these numbers through substitution, we got a few answers that we're going to share with you. Internal force between joints 1 and 2 was 800 newtons compression. Internal force between joints 1 and 3 was 600 newtons compression. Between joints 2 and 3, we had 480 newtons of tension, which basically is the opposite of compression. And our reaction forces were, on joint 3 in the Y direction, we had 360 newtons. Joint 2 in the X direction, we had 0 newtons. And joint 2 in the Y direction, we had 640 newtons.
So, as we just figured out, we have the internal force between joints 1 and 2 and the internal force between joints 1 and 3 are in compression. This means that the internal forces are pushing on the joints. So they're pushing into the joints. Opposite of that is tension, which we found out is in the internal force between joints 2 and 3. This means that the internal force is pulling away from the joints. So that is it for our discussion of the static analysis of a complete truss. So for Team PCs, I'm Josh Isaacson.
And I'm Justin Evan Shane, and this is us signing off.